By the end of this lesson, you should be able to understand the characteristics of the atmosphere and how they change with altitude. You will also learn about static and dynamic pressure, temperature, density, and the International Standard Atmosphere, commonly referred to as ISA. The lesson concludes with explanations of airspeed and its various categories. The atmosphere is the medium in which aircraft operate. It is the properties of the atmosphere, that is, the mixture of gases which comprise air, that generate the required lift force when it is acted on by the shape of a wing. The most important property of air is its density. If air density decreases, the mass of air flowing over an aircraft in a given time will decrease. The concept of mass flow is a useful one to keep in the back of your mind when considering principles of flight, as thinking of airflow in terms of kilograms per second can help with understanding. Thus, if a given mass flow is generating the required lift, then a drop in density will reduce the mass flow and the lift. To maintain the required lift if density is decreased, the speed of the aircraft through the air must be increased, and the increased speed of the airflow over the wings can restore the mass flow and the lift to its previous value. We have already talked about mass flow of air. Air may not have a great deal of mass compared to, say, metal, or even a human body, but it is significant. A mass of moving air has considerable kinetic energy. Think of the damage done by hurricane force winds or tornadoes. Air is also a compressible fluid, and is able to flow or change its shape when subjected to even small pressure changes. Being fluid, air will always flow from high to low pressure. Like a tube of toothpaste, even with the cap on, squeeze the middle and the toothpaste moves to the ends where you're not squeezing it. Another example is air being released from a toy balloon. Unlike toothpaste, though, the viscosity of air is very low, and even small forces are easily able to move the molecules relative to each other. The part of the atmosphere in which most aircraft fly, that is up to about 40,000 feet, undergoes gradual changes in its characteristics with height. Since air is compressible, the lower layers contain by far the greater part of the atmosphere's mass. Atmospheric pressure, referred to as static or ambient pressure, decreases steadily with increasing altitude, but temperature falls progressively only to about 36,000 feet, above which it remains more or less constant throughout the stratosphere. Static pressure is the pressure exerted by the air of the atmosphere on any object anywhere in the atmosphere, and can act in any direction. Static pressure is measured in newtons per square metre, and for these lessons is given the symbol lowercase p. Key points about static pressure are that static pressure is the result of the weight of the atmosphere pressing down on the air beneath. Static pressure will exert the same force per square metre on all surfaces of an aeroplane. The lower the altitude, the greater the force per square metre. It is called static pressure because of the air's stationary or static presence. An aircraft always has static pressure acting on it. Newtons per square metre is the SI, for Système International, unit of pressure. 1 Newton per square metre is called a Pascal, but since this is rather a small unit, the hectopascal is used in aviation and meteorology. Hecto is from the Greek for 100, and 1 hectopascal equals 1 millibar. Static pressure at any particular altitude will vary from day to day, and averages about 1,000 hectopascals at sea level. In some countries, notably the USA and Canada, pressure and altimeter settings are given in inches of mercury, and the equivalent sea level pressure is 30 inches. The unit for temperature is the degree Celsius if measured relative to the freezing point of water, or temperature Kelvin if measured relative to absolute zero, which equates to minus 273 degrees Celsius. 0 degrees Celsius or centigrade is thus equivalent to 273 Kelvin. On some older aircraft, some instrumentation may be calibrated in degrees Fahrenheit, a scale in which freezing point is 32 degrees and boiling point 212 degrees. The unit of density is kilograms per cubic meter, and the symbol used for density is the Greek letter rho. Density can be defined as mass per unit volume, or you could think of it as the number of air particles in a given space. Density varies with static pressure, temperature and humidity. Density decreases if static pressure decreases, if temperature increases, and if humidity increases. This last factor will be considered later. The first two factors can be otherwise expressed in accordance with the ideal gas law, that density is proportional to pressure and inversely proportional to temperature. The formula states that pressure over temperature times density is a constant, or, to rearrange it, density is proportional to pressure over temperature. Density decreases with increasing height because of diminishing static pressure. The drop in temperature with height will tend to increase density, but the pressure-related decrease is dominant. The values of temperature, pressure and density are never constant in any given layer of the atmosphere. So, to enable accurate comparison of aircraft performance and the calibration of pressure instruments, a standard set of values has been adopted. This standard atmosphere represents mean or average properties and is defined by the International Civil Aviation Organization, ICAO. The International Standard Atmosphere, or ISA, assumes the following mean sea level values: temperature 15 degrees Celsius, pressure 1013.25 hectopascals, commonly referred to as 1013, density 1.225 kilos per cubic meter, and a uniform temperature lapse rate of 1.98 degrees C per 1,000 feet, up to 11,000 meters, or 36,090 feet, with a constant temperature of minus 56.5 above that level. A tabulated version of ISA is shown on the screen.